Good afternoon, everyone. So let's wait for 1 or 2 more minutes because people are still joining. Okay, I think we should slowly start. So good afternoon, everyone, at least for those who are in the Netherlands or in Europe. So my name is Andy Pimentel, and I'll be moderating this session. So welcome to this new edition or another edition of this series of IPN Colloquia. As a reminder, so we are organizing these colloquia to celebrate the 25th anniversary of IPN this year, or actually also last year. And it gives me enormous pleasure to introduce the speaker of today, who is Paula Herber. And she's a full professor and head of the Embedded Systems Group and managing director of the Computer Science Department of the University of Münster in Germany. But also since 2021, she's also part-time full professor at the University of Twente in the Netherlands in the formal Methods and Tools group. Her main research interests include quality assurance for embedded systems, test automation, and formal methods. And she's best known for her contributions to formalization of industrial used system design languages such as System C and Simulink, and for advancing techniques that improve the practical applicability of formal methods for embedded and cyber physical systems. And in today's talk, she will talk about why safety in embedded systems need formal methods. But before we give her the floor, so if you happen to have an urgent question during the talk, you can raise your virtual hand and we give you the floor so we can enable your video. But of course, after the talk, we also open the floor for all kinds of questions and do it in a similar fashion. So you can raise your virtual hand and we can enable your video and your audio. Now, without further ado, I would like to give the floor to our speaker of today, Paula. Please go ahead.
Thank you very much. Thank you for the introduction, and also thank you very much for the invitation. I feel very honored to speak in this IPN colloquium. What I want to do today basically is to persuade you that we need formal methods to design safe embedded systems. And I will start with the motivation for this. So embedded systems, as many of you probably know, are systems that are embedded into a technical environment and interact with this environment via sensors and actuators. And such systems surround us everywhere in our daily lives, ranging from smart homes over smart cities to smart logistics, and from smart factory robots over medical support systems to self-driving cars. And although embedded systems are historically comparatively small, their complexity is increasing very much. So a Boeing 787, for example, contains approximately 15 million lines of code, and a modern car even more than 100 million lines of code. And at the same time, these systems are often safety critical, which means that a failure may result in enormous costs or even endanger human lives. And this naturally makes it crucial to ensure their correctness under all circumstances. However, in practice, even such safety critical systems often fail. So, for example, in 2015, the US Aviation Authority reported on a software bug in the Boeing 787, which was actually an integer overflow in one of the generator control units, which led to a complete shutdown of the whole generator unit every 248 days without a system restart. Fortunately, that bug was detected before anything bad happens, but there are also cases where failures of the control software can have really severe consequences, as for the Tesla bug in 2018, for example, or as tragically illustrated by the death of a pedestrian caused by a software fault of a self-driving Uber, the near flooding of Amsterdam in 2023, or most recently by Waymo having problems with self-driving vehicles hitting into road barriers. So these things happen, although the responsible companies and manufacturers of course have serious quality assurance in place, and the systems are extensively simulated and tested. So Edgar W. Dijkstra, probably the most famous Dutch computer scientist, already said in 1972 that testing can be used to show the presence of bugs, but never their absence. And this is due to the problem that with testing, one always considers only a selection of possible inputs and possible executions, but we do not get any information about untested scenarios, so it is inherently incomplete. So the question is, how can we ensure safety in all cases? And the potential solution, the potential answer to this is, of course, to use formal methods. And in the remainder of this talk, I will first explain how formal methods achieve this, so how they achieve safety in all cases for those of you who are not that familiar with formal methods. And for this, I will briefly walk through the key ideas of two famous examples of formal methods, namely model checking and deductive verification. And while this should give you an idea what formal methods can do, I will then also talk about the challenges we meet when we try to use formal methods for embedded systems. And then in the last part of my talk, I will show a few examples from the research of my group, my collaboration partners, and me, what we have done to address these challenges and to increase the applicability of formal methods for embedded systems. In particular, I will show some work we have done to integrate formal methods into the design process, an approach to integrate ideas from deductive verification and model checking to meet the scalability challenge. And finally, if time allows, I will also briefly show an approach we have developed to enable the safe integration of learning components into the formal verification process. And then I will conclude my talk and give an outlook on open research problems and future work. So let me start with an introduction to the key ideas of formal methods. So the goal of formal methods is to provide an unambiguous specification of the system and desired properties, also called requirements, and to prove that the system behaves exactly as intended under all possible conditions. The general approach to achieve this with formal methods is to use formal modeling techniques, that is, modeling techniques with mathematically precisely defined semantics. Examples for such modeling techniques are Kripke structures, automata models, and formal logics, with which a system and its requirements can be precisely and unambiguously described. If we have such a precise description, the correctness of a system in the sense that it behaves exactly as intended under all possible conditions can be verified using mathematical reasoning techniques such as model checking or deductive verification. And I will start with the idea of model checking. The idea of model checking is basically that we have a formal model M of the system under verification, for example, a graph describing possible states, and a formula phi describing desired properties in temporal logics, for example, that some formula P should hold always globally. A model checker takes such a model and such a formula and checks whether the formula holds in every state in the given model. And if this is the case, the model checker returns the result that the property is satisfied. If the property does not hold, it provides a counterexample, for example, a path through the model that violates the given property. Yeah, so this is the idea from a very black box view. So we want to look into this. And for this, we look at the underlying formalism that is typically used to describe the system under verification for model checking. And this is a Kripke structure. So a Kripke structure is a tuple, ST S0L, where S is a set of states T is a transition relation that connects source and target states. S0 is a set of initial states, and L is a labeling function that assigns atomic propositions to each state. That is, L tells us which atomic propositions hold in a given state S. As an example for this, you can imagine a simple controller of the traffic lights at a train crossing. The traffic lights are initially red, and whenever a train comes, the controller switches the smaller train light from red to green. And if no train is coming, the controller switches the traffic light for cars first to red, yellow, and after some time out to green. It stays green until a train is approaching again. And if this happens, the traffic light for the cars is switched first to yellow and then again to red. So to formalize the traffic light controller as a Kripke structure, the circles are interpreted as states and the arrows as transition between these states. Thus, the set of states is simply S1 to S5, and the set of transitions between these states corresponds to a set of pairs of source and target states for each arrow. And the initial state is S1. And the atomic proposition in this example can be used to capture the current color of the traffic lights, for example, that both the car and the train light are red in S1. Yeah, so I hope you can see with this example that with a Kripke structure, we can precisely and unambiguously describe the behavior of the traffic light controller. And we can imagine from this simple example already that we can also map arbitrary software into a Kripke structure by using the program counter and program variables as state. And then each statement in the program can be mapped into a transition relation that captures how we move from one line of code to the next. And also the behavior of a hardware circuit can be mapped into a Kripke structure, where the register values are the current state and the combinatorial logic defines how we transition from one state to the next. And of course, the automata and state machine dialects you might have met in the past can also be translated into a Kripke structure. So with Kripke structures, we have a simple but powerful and precise means to capture a system's behavior. And to argue about the properties of a system with respect to its possible behavior, we use the concept of a path within a Kripke structure, where a path is just a sequence of states that are connected by the transition relation. So, for example, in our traffic light controller, a possible path is that we can move from S1 to S2, back to S1, and then via S3 to S4 and S5, and back to S1 again. Paths are very useful because they describe possible behavior. To specify the intended behavior, that is the requirements, model checking based approaches typically use temporal logics. Temporal logics are logics that express temporal properties over paths and states using path quantifiers such as on all paths or there exists a path, together with temporal operators such as in the next state, until, globally, or in some future state. An example of a temporal logic is the computation tree logic CTL, which provides the usual Boolean operators and combinations of path quantifiers and temporal operators to define properties over paths and states. Such as on all paths in the next state phi holds, there exists a path where in the next state phi holds, on all paths phi holds until psi holds, and so forth. In our example of the traffic light controller, we would like to express properties such as on all paths globally, that is, in each state along each path, the traffic light of the cars and the traffic light should not be green at the same time. This is a classical safety property, which expresses that something bad should never happen. And we can also express reachability properties in CTL. For example, that there should be at least one path where the traffic light of the cars become green somewhere in the future. And we can also express liveness properties. For example, that whenever a train is coming, the traffic light for the trains should eventually become green on all paths. In their famous model checking book, Clark, Gromberg, and Pellet have stated that temporal logics have proven to be useful for specifying concurrent systems because they can describe the ordering of events in time without introducing time explicitly. And today, temporal logics with various dialects and extensions are used very widely for the specification of software and system requirements. Yeah, so we have a way to describe the system with the crypto structures and a way to specify the requirements with the temporal logics. And we can use this now for model checking. So to check whether a system described by a crypto structure actually satisfies a given temporal logic formula, we can use model checking algorithms. And the underlying idea is typically just that we unfold the whole state space of a given crypto structure as a computation tree and check whether the desired properties holds in each state. For reachability and liveness properties, we can use fixed point algorithms to check whether a property holds along certain paths. So, for example, to check whether e.g. phi holds, so there exists a path where globally phi holds, we can initially label all states that satisfy phi with e.g. phi, and then delete the label if no successor state is labeled with e.g. phi until we reach a fixed point, that is until nothing changes anymore, and then only paths where phi holds globally along the path will still be labeled with e.g. phi. So yeah, we have the solution, and such an algorithm is also called a greatest fixed point because we start with an over approximation of all the states satisfying e.g. phi and then refine it until only states that satisfy e.g. phi are left. Yeah, so this is the key idea of model checking. Of course, I could talk about more advanced techniques and optimizations a lot longer, but I hope you got the main idea how this works. And to give you an idea of the practical relevance of model checking, I want to very briefly summarize the history of model checking. So model checking was invented in parallel, actually, by Clark and Emerson and by Quay and Sifakis in 1981 already. They get a Turing Award for this in 2007, by the way. And in the early years, model checking was already successfully applied to smaller applications. Yeah, but then in the 90s, also to more advanced applications like a cache coherence protocol, flood control software, and several real-time protocols. And the acceptance of model checking in industry gained a lot of traction in the late 90s when equivalence checking became standard in many hardware synthesis tools. And since then, model checking is an integral part of standard hardware design tools, at least. Yeah. Of course, since 2000, many applications beyond synchronous hardware have also been considered with model checking. Marta Kwiatkowska and others developed Prism, for example, a model checker that can cope with probabilities for randomized distributed algorithms. The SLAM model checker was applied to Windows device drivers and C++ libraries. SPIN was successfully used for space missions, and more recent work by Cimati and others reports on the use of the OCRA framework for automotive systems, nuclear power plants, or in the railway domain. Yeah, beside these success stories, I would say, formal methods are increasingly required or recommended in safety standards for automotive avionics and industrial control systems. And today, many companies actively use model checking, for example, Bosch, Airbus, Collins Aerospace, and many more, just to name a few. So, to summarize, the idea of model checking is to walk through the state space of a model M and check a temporal property phi in each state. And the main advantages of model checking are that it is fully automatic, provides counterexample for debugging, supports concurrency as well as both synchronous and asynchronous systems, both hardware and software basically, and extensions are available for real-time probabilities and statistical model checking. So this is really cool. Unfortunately, model checking also has a major downside, and this is the so-called state space explosion problem. With many variables, concurrent processes, or other forms of complex behavior, such as learning components, for example, the state space just becomes too big to fully explore. In addition, model checking is not compositional. If you add a new process or a new signal to a system, you have to compute the new states of the composed system by combining each state of the old system, which each state of the new process or signal, which leads to an exponential growth in the number of states. This is a serious limitation which impedes the use of model checking for many complex systems. Of course, there's a lot of work to tackle this problem and to increase the scalability of model checking, for example, using symmetry reductions, abstract interpretation, partial order reductions, invariants, and so forth. However, these approaches only reduce the state space explosion problem and cannot solve it completely. Yeah, an alternative approach that promises to be more scalable by leveraging the power of induction is deductive verification. And I also want to briefly introduce this. So the key idea of deductive verification is that we establish system correctness through rigorous mathematical reasoning and logical proofs using inference rules. As inference rules are really at the core of this, I want to show you an example. And this is the inference rule for loops from the Hawk calculus. The idea here is that we can prove by induction that some invariant I holds after the execution of a given loop if we can establish that this invariant I is preserved by each execution of the loop body S. In our proof, we can make use of the fact that the loop condition B must hold within the loop and cannot hold after the loop. So we have AND B within each loop iteration, at least at the beginning, and not B after the loop. So let me illustrate how this works with a small example. So this little piece of code here computes the sum of the numbers from 1 to n. And if we want to describe formally what it does, we can say that under the precondition that n is greater or equal to 0, the post condition is that sum actually holds the sum from 1 to n. To prove that this is correct using loop induction, we need to find an invariant that holds before and after each loop iteration and is strong enough to imply the post condition, so really helps us to prove the desired properties. In this example, we can define as an invariant that before and after each loop iteration, the variable sum will contain the sum from 1, not to n, but to I minus 1, because that's what we've already done in each loop. And that I will always be less or equal to n plus 1, because we know that the loop will be aborted if I reaches n plus 1. In addition, we know that when we enter the loop condition B will hold, and that not B will hold after the loop is aborted. The inference rule now says that if I holds before the loop and is preserved by each execution of the loop body, then I and not B will hold after the loop. So we have to check, sorry, that was one step too far. So we have to check that I holds before the loop. You can easily check that for yourselves by just replacing I and sum with the actual values 1 and 0, which leads to the equality 0 equals 0, which is obviously true. And then we have to check that I is preserved in each loop iteration. And we can easily see that if we increase sum with 1 and I with 1 in the equation of the loop invariant, this cancels each other out. So the sum term is again true. In addition, the loop condition ensures that I is still less or equal to n plus 1 if we increase I by 1 within the loop. And then finally, if we conjunct the invariant with not B, we can see that I equals n plus 1 actually after the last loop iteration, and thus the post condition is implied. And this is what we wanted. We have formally proven. I didn't use all the rules you usually need to use here, but I hope you understand the underlying principle. And we have proven using mathematical reasoning and inference rules that this piece of code actually satisfies the post condition. And the great thing is that we have done this without looking at any specific values for sum or for n. So we did not unfold the state space like model checking does. And this is why deductive verification scales well, even for non-terminating systems with control loops. At the same time, this kind of verification is very flexible. We can define and use much more expressive logic than with model checking and develop appropriate proof calculi. The challenge, of course, is to find the right invariants, which are much more difficult to find for reactive, concurrent, and hybrid systems than in our example here, of course, and can generally not be found automatically. So the scalability of deductive verification comes at the price of the manual definition of invariants. Yeah, so I hope this gave you an idea of how deductive verification works now, and also will give a very brief account of the history of deductive verification. The theoretical foundations were led by Hoare and Dijkstra already in the 60s and 70s with the Hoare logic and Dijkstra's weakest preconditions, which enables us not only to relate pre and post conditions like the Hoare calculus does, but also to compute the weakest precondition for a given post condition. And this was a stepping stone for the first automation approaches, which were in particular enabled by the ideas for modular verification and design by contract developed in the 80s and 90s. And then in the 90s, first automation efforts were done with theory improvers like ACL2, but these tools were proof assistant that still required heavy user interaction. And the real golden age of deductive verification happened then since 2000, when a variety of mature program verification tools has been developed and is still actively maintained. For example, the key tool, Daphne, Framacy, Y3, or Vercor. And the feasibility of formal methods has also been demonstrated in this time by several fully verified system software like CompCert, a fully verified C compiler, and Cell4, a fully verified microkernel. In the last decade, in the last 2 decades, maybe even, automation and scalability of these tools has been immensely increased by using SMT solvers as verification backends, and also tools for more complex systems have been developed. So, for example, Chimera X for hybrid systems that are described by differential equations. Today, as for model checking, industrial users of deductive verification also include many big names from the industry, such as Thales, Scania, Bosch, Daimler, and many more. So this showed the success of formal methods. But yeah, well, why do I still need to persuade you that we need formal methods? And why do these things happen I mentioned in the introduction? The problem is still that formal methods in general, due to their expensiveness, are only used in a very small portion of the immense amount of software that is developed every year, and also in embedded systems. And the main reason for this is that there is a significant gap between what is possible in theory and what actually happens in typical industrial applications. In theory, systems can be automatically verified for all possible input scenarios and for all possible behaviors. However, due to their expensiveness, formal methods are typically only applied to small, crucial components or in high levels of abstractions. And as a result, in industrial practice, where a modern car already contains more than 100 control units running more than a gigabyte software, the quality assurance techniques of choice are still simulation and testing. This, however, has the major drawback, of course, that only a small selection of input scenarios is considered, and software bugs can be overseen, as happened with the Boeing 787 or with Tesla. And I would say that there are 3 major barriers that preclude formal methods and algorithms from being applied to industrial system design on a regular basis. First, formal methods require a full formalization of the system under verification, but the models and languages that are typically used in industrial design processes typically only have informally defined semantics. Second, while there exists fully automatic verification techniques such as model checking or SMT solving, these techniques do not scale well for larger systems. Deductive verification have the potential to overcome this problem and to scale better, but they impose a very high manual specification and verification effort on the designer. So these barriers prevent formal methods from being applied in industrial design processes in general, and they are especially pronounced in embedded systems, because embedded systems come with some particular challenges for the application of formal methods. And these challenges are mainly imposed by their heterogeneity and their complexity. So for embedded systems, a diverse variety of heterogeneous models and languages is typically used, for example, because they consist of deeply intertwined hardware and software, because they combine discrete control with a continuous environment, synchronous with asynchronous parts, and so forth. And this means that a variety of models of computation are involved in embedded system design. And to further complicate things, as I already mentioned, the semantics of the models and languages that are used are typically not formally well defined. With respect to the increasing complexity, first of all, embedded systems are already inherently pretty complex because they are concurrent, reactive, generally should not terminate, and control a technical environment that evolves in real time. And in addition, in recent years, the complexity of embedded systems is further increasing, not only because we have started to connect a huge number of devices, but also because the environments of embedded systems are getting more complex and more dynamic when we go from a classical temperature control system or a factory robot with one particular purpose to self-driving cars or smart manufacturing systems. Yeah, and to cope with the heterogeneity and complexity of embedded systems, model-based development has become more and more widespread during the last 2 decades. And in particular, for embedded systems, so-called system design languages are often used. That is, languages that support multiple models of computation and enable analysis and simulation during the whole development process with executable system models. And in the area of embedded systems, 2 widely used system design languages are System C for the design of integrated hardware-software systems, and MATLAB Simulink for modeling and simulation of complex dynamic systems. And just to give you a quick impression how this looks like, who are not from this direction, the system design language System C basically extends C++ with constructs for the description of hardware, for example, with time, reactivity, and hardware data types, and with structural modeling constructs such as ports and channels. And as an extension of C++, System C is a classical control flow-oriented language, and Simulink, on the other hand, is a data flow-oriented language, which basically extends classical block diagrams with means to model the differential equations of dynamic systems, for example, with integrators and complex mathematical functions of the underlying MATLAB library. Both Simulink and System C are widely used in the industry and provide very good support for modeling and simulation of complex embedded systems. However, both have only informally defined semantics, and as a consequence, their correctness and reliability can be validated using simulation and testing, but not via formal verification. Yeah, of course, open problems are also opportunities for research. And in our research, we have addressed this problem by developing techniques to formalize the semantics of industrially used design languages. So the question we have addressed in this part of our research is how to get from an informal description of the requirements and the system under verification to a formal verification process. And a key idea we exploit to overcome this problem in our research are what we call domain-specific abstractions. And the idea is that on the one hand, we can use domain-specific abstractions to define formal encodings of the semantics of informally defined languages to enable an automated formalization, that is, an automated transformation of informally defined system descriptions into a formal system model. And on the other hand, we can also use domain-specific abstractions to define reusable specification mechanisms that help the designer to develop formal specifications that are needed for the verification, for example, assertions and invariants, but also safety, timing, and resilience properties or contracts for learning components. But let me get back to this later. And first, let me briefly summarize what we have done to encode the semantics of industrially used design languages. We have done this for both System C and Simulink. And to formalize the semantics of System C, we have developed semantics encodings that enable automated formalization from System C into the input languages of several verification backends, namely into the UPAL model checker, which is especially well suited to verify timing properties and synchronization between processes, into the input language of the CPA checker, a software model checker which enables configurable program analysis, the Euclid SMT solver, which is particularly well suited for bit-precise hardware verification, and most recently, the deductive verifier VERCOR, which enables powerful mathematical reasoning. All of these verification tools can be used to verify properties for all possible input scenarios and for an unbounded time, and some of them, like Vercor and Euclid, even with unbounded parameters. Also, all of them give us some hints for debugging if the verification fails, for example, a counterexample or a failed assertion. To formalize the semantics of Simulink, we have developed a semantics encoding of Simulink's execution semantics, again in Euclid, which enables SMT solving, but of course only works for discrete subset of Simulink, and into the differential dynamic logic, which enables interactive deductive reasoning also for hybrid systems using the theorem prover Chimera X. And more recently, we have also developed an encoding with stochastic hybrid automata, which enables quantitative reachability analysis and statistical model checking in the presence of uncertainty using tools such as the MODIS toolset or Realist. The main advantage of all these works is that our semantic mappings define formal semantics for the considered industrial design languages and enable a fully automatic formalization. Of course, the formal languages we use do not have the full expressiveness of System C or Simulink. So they only support a clearly defined subset. However, if a given design is within the supported subset, we get access to existing mature and powerful verification tools. We have successfully verified a number of case studies using our automated formalization, for example, an anti-slip regulation and anti-lock braking system, a universal asynchronous receiver transmitter provided to us by Metamorph, a model of ARM's advanced high-performance bus provided by Carbon Design Systems, a generic infusion pump taken from the OpenGIP project, and a multi-object distance warner provided to us by partners from the automotive industry. What is interesting to note is that in 2 case studies which have been provided to us by industrial partners and which have undergone extensive simulation and testing procedures already, we still detected serious bugs like a deadlock, a null pointer access, and an integer overflow. So these were errors that only occur in rare corner cases, of course, and thus are very hard to detect by simulation and testing alone. But these are serious bugs in the sense that the whole system will fail if these rare situations occur. I think this demonstrates that formal methods can really help to prevent such bugs before the systems are put into operation. But still, the scalability of such verification techniques is an issue, of course, due to the state space explosion problem of model checking and the manual effort necessary for deductive verification. One approach we have developed to partially overcome this problem is an approach that combines the strengths of deductive verification and model checking. We have originally developed this approach for System C, but have recently also applied it to software that runs on top of a real-time operating system. And in this work, the main idea was to address the problem that the execution semantics of embedded systems crucially depends on the underlying real-time operating system, or short RTOS. Program verification frameworks typically abstract from the RTOS completely, and model checking based approaches that address the execution of RTOS-based software have the problem that they do not scale well with increasing state or data spaces, of course, in particular, if process interleavings and dependencies are taken into account, and approaches based on deductive verification, on the other hand, have the potential to scale better due to the mathematical reasoning power and modular verification approach, but impose a very high manual effort to define the necessary assertions and invariants. So the key idea of our approach here is to use an integrated approach where we complement a deductive verification approach with a so-called reachable abstract states invariant, which is automatically computing using a model checking style abstract interpretation. And the foundation of this work is, again, an automated formalization. We have developed a semantics encoding of a particular real-time operating system, namely the industrially widely used FreeRTOS, which enables us to automatically transform FreeRTOS applications into the prototypal verification language, which is an input language of the deductive verifier Vercor. And Vercor then enables deductive reasoning about concurrent software, but of course requires invariants and assertions which need to be manually defined. And to reduce the manual specification effort, we have developed reusable specification mechanisms that ease the definition of both local and global properties, and in particular enable the automatic generation of a reachable abstract states invariant, which we call the RASI. So local properties are properties that describe functional behavior at a local level by solely using local information. So these are properties that can be captured naturally using method contracts or local assertions. And an example for this is the correct choice of speed in an adaptive cruise control system locally when the distance to the lead car and the target speed are already locally available to a process. In this example here, we decrease the speed whenever we are getting close to the lead car, or if we are driving faster than the target speed, and we increase speed whenever the distance to the lead car is big enough and we have not yet reached the target speed. Such local properties can very efficiently be verified using the modular reasoning techniques of Vercor. However, while such local properties solely depend on the local information within one task, global properties are properties that depend on task interactions and events. So they cannot be defined solely within one task, but require information from other tasks. So for example, if we want to ensure that the main control unit of an adaptive cruise control system always reacts to sensor inputs within a given time limit, we need to start a timer within the sensor task whenever new data is received, and then check the timer within the main control unit. While local properties can be verified very efficiently with Vercor, such global properties are much more challenging because they require global invariance about the relation between tasks and events. A simple example of such a global invariant is deadlock freedom, where we specify that we do not get into a state where all tasks are waiting for an event, but no event is scheduled anymore. This is an example of a global invariant, but it does not provide us with the necessary information we need to verify timing properties or other global properties that depend on the order of execution and timing of tasks. So to define the necessary global invariance for this can actually be quite challenging because we need the information that the control task is actually always executed whenever new sensor data is available, for example. And this information is not locally available. So to address this problem and to ease the verification of such global properties, we have introduced the concept of the reachable abstract states invariant, or short RASI. And the basic intuition here is that we capture reachable states in a global invariant, but capture only task and event states and abstract from data completely. With that, we can restrict the verification to the reachable abstract state space and make the information about task interdependencies and interactions locally available. Technically, we compute the reachable abstract states invariant by exploring the abstract state space of a given design and building one big disjunction between the reachable abstract states. So as you can see here, our RASI basically says you can be in a state where the sensor is running and the control unit is ready to execute. The obstacle event has not been notified yet. The timeout event will elapse in 20 milliseconds and the only runnable state is the controller task. Or you can be in a state where the sensor task is waiting for the timeout event and the controller task is running, and so forth. With this information available, the necessary invariants for global properties are much easier to define, and this can automatically be computed. But of course, as we do a model checking style state space exploration to compute the reachable abstract states, it is also again subject to the state space explosion problem. To alleviate this problem a bit, we have developed an automated refinement process where abstract interpretation is used to systematically select and add data variables that reduce the number of possible task interleavings to the abstraction. For example, to keep track of the number of items in a queue can actually help to reduce the number of interleavings, because we then know at which points of execution the read task can actually not read any more items from the queue. However, scalability is still an issue, and we have investigated the scalability and the feasibility of the approach with an adaptive cruise control system where two sensors measure the distance to the lead car and the current speed. The user set the target speed through a hardware interrupt, and a central control unit then chooses the desired speed for the motor control accordingly. And for our experience, we have transformed this case study into PVL, of course, automatically generated the RASI, and then verified both local and global properties. And as you can see here, the verification was successful, but you can also see the scalability issue. If we just add a few dummy tasks, so +1, +2 is just adding dummy tasks that actually have no functional behavior, but just increase the number of possible task interleavings. And you can see that the verification is still successful with up to 3 additional tasks, but does not terminate within 72 hours with 4 additional tasks, indicating a state space explosion problem. However, on the plus side, the manual specification effort was only 1 or 2 hours, which is a great reduction compared to other works that use deductive verification. And we achieved this reduction by integrating the strengths of a model checking style abstract interpretation into a deductive verification process. And I think this idea has quite some potential. Okay, I've already talked for a while, so I will go over the last part of my talk very quickly and only sketch the key ideas of our approach for the safe integration of learning components. So this work builds on existing automated formalizations of Simulink with the differential dynamic logic. And to safely integrate learning components into Simulink models, we have developed an approach where the safe actions of reinforcement learning agents are described by a contract. And I will illustrate this real quick with a small example and then wrap this talk up. So in this example, a factory robot uses reinforcement learning to reach dynamically assigned workstations while it has to avoid moving obstacles, which we also call opponents, A and B. And the main safety requirement in this case study is that the robot should not crash with the opponents. So the distance between the robot and both opponents should always be greater than some predefined safety threshold. I do not have the time to explain the details of the Simulink model of this, but the interesting point is that for the verification of the Simulink model, we can replace the RL agent from the Simulink model by a contract that defines safe actions. And the contract basically just says that under the assumption that we have a non-negative sample time and that the opponent is not driving backward, the RL agent either stops, which we always consider to be safe, or if it drives with a positive velocity, then the distance to the opponent minus the maximal movement of both the RL robot and the opponent within one sample time towards each other is still greater than the predefined safety distance. So this contract replaces the RL agent for system verification instead of fully formalizing the learning process. So for verification, for the formal verification process, we just use this contract instead of the learning agent and verify the system under the assumption that the RL agent adheres to its contract. Of course, we then still need to make sure that the RL agent actually adheres to the contract at simulation or runtime, and we do this by automatically generating a runtime monitor from the contract, as has been proposed by Fulton and Plaza already. Yeah, to reduce the key idea, to reduce the necessary manual effort for this, we have also proposed reusable contract patterns, which basically exploit the systems where an RL controller controls continuous variables always look very similar, but I will skip this in the interest of time, and I only will mention that we have verified quite some case studies from the Simulink RL library using our approach, including an intelligent temperature control system, an intelligent water tank, our factory robot, an adaptive cruise control system, and an intelligent distributed water control system where the pumps are subject to stochastic failure. Yeah, so let me conclude this talk. I hope I have persuaded you today, if you were not already persuaded before, that embedded systems need formal methods, or at least that their safety and dependability can significantly benefit from formal methods. However, the application of formal methods to embedded systems is challenging, in particular due to the heterogeneity, the informally defined semantics of industrially used languages, and due to the complexity that is inherent to embedded systems due to their concurrency, reactivity, and real-time dependency. So research is needed to overcome these challenges, and I hope you have shown you some impressions from our own work on this, in particular that semantics encodings can enable the automated formalization of industrial design languages and give access to existing verification tools, and that reusable specification mechanisms can help to increase scalability and to reduce the manual verification effort. This is not the end of this, of course. There are several open challenges and open research questions. One is that the automated formalizations only support subsets of the industrially used design languages, so not all the programming features industrial designers typically use are covered. Furthermore, of course, more work is needed on increasing the usability and scalability of formal methods for embedded systems. And another challenge, which is has gained very much interest by the industry in recent years, is to go beyond qualitative safety properties and to also address quantitative aspects. Yeah, and with that, I conclude my talk, and I'm very happy to hear your questions.
Thank you so much, Paula. So thank you for this very nice talk. So I hereby open the floor for questions. So is there anyone who has a question for Paula? So maybe I can start with a question. I think you already partly kind of raised the issue. So I mean, time is, at least for some embedded systems, a functional requirement, where it is a non-functional requirement in most other systems.
Yes.
And I mean, validating or verifying, let's say that a piece of software, for example, meets its deadlines and things like that, is not that easy. I mean, to do it in an integrated fashion. So to validate the functionality on one hand, but also the timing behavior. So what would be needed, do you think, in this embedded world to kind of make a uniform approach to both, let's say, validate or verify that both the timing behavior as well as, let's say, the more traditional functional behavior of a system?
Yeah, thanks. That's a very good question. I mean, the work we are doing around FreeRTOS, for example, already takes time into consideration, and also for systems C and Simulink. I mean, the work we do always considers time and enables you to verify timing properties also, but of course, time is one of the major reasons why this scales so badly, right? Because it has so many potential behaviors. And
Yes.
Although we provide some solutions, of course, we require that time is modeled somehow, right? So in our approach where we work with FreeRTOS, we require that worst case and best case execution times are basically available from somewhere. and I think there's a lot of work on how you can do schedulability analysis, for example, or static timing analysis to have a more focused approach to work with time. And I think these ideas can be integrated into the formal verification process, but this still then leaves the question open: how do you know the timings in the first place? So for one execution or one gate, how do you get these execution times? And I think that the many approaches that exist need to be harmonized and brought together there, because we have a lot of pieces solving
Exactly.
some of these problems somewhere, but few people target how they actually come together in the real design process.
Yeah. Okay. Thank you. Any question from the audience? Please raise your hand if you have a question.
Well, maybe I can ask a question.
Sure, you can.
Raise my hand. Yeah. Yeah. Well, of course I know, and we've been working on this deductive verification work together, but What I was wondering, because you talked also about your model checking work, and if there would be ways where we could actually combine this in some way and get to a cooperative verification approach so that we can scale things even further. So I would like to know what you think about that.
Yeah, yeah. I mean, there are, of course, approaches that go into this direction, but I think that a fundamental challenge for this are the very different concepts, how systems are described for model checking and for deductive verification. I mean, there are some discussions you are probably also aware of about, for example, combining trace properties and pre-post conditions. But to me, this doesn't answer the question how to really combine the underlying techniques in a meaningful way. I mean, of course, there are simple things you can do, like verifying one component with model checking and use the result in a deductive verification approach. This has been done, I think, in the 90s, or at least in the 2000s already, by people. This is easy, but that does not really integrate the techniques. And usually, if you have a formalization that enables deductive verification, the components that are simple enough to be handled with model checking can also be automatically discharged by today's theorem provers. So this is not the part where it gets interesting. And yeah, for the more interesting part, where I think that techniques like we have worked on, right, like using model checking style abstract interpretation in a theorem prover, or also from the other side, I mean, modern model checkers incorporate a lot of ideas based on deductive verification, for example, like this incremental invariant building. And so ideas are used in both communities, but I'm not sure it is really possible to bring the fundamental concepts together because of the different ways systems are viewed in each concept.
Okay, yeah, thanks.
Okay. Any other questions from the audience?
Yeah,
Rodrigo. Let me see if I can.
Yes, can you hear me?
Yes, we can hear you.
Okay. Thanks for the nice talk. So I have a question on the part about the specification. So you touched about the situation in which, like, you start from a system that has an informal semantics, right? And the model is defined on a language that has informal semantics. And you mentioned that you collaborated with a lot of industrial partners. So my curiosity is, based on this experience, do you see that in industry, people might be open to considering considering languages with formal semantics to start with, or is they really this is not the direction that they're considering? Is really just like we have to somehow handle the fact that we have to start from informal semantics, informal description of the system?
Yeah, I think right now that's a very interesting question too. I think right now there is a gap between what the languages with the expressiveness and the programming features and modeling features you have in industrial languages, and the ones that are supported by formal tools. And personally, I hope that with a lot of more research, we are moving towards evolving formal methods more into the direction to support these expressiveness and programming features like pointers and dynamic process creation and things like that, without becoming completely unreadable. So, I mean, there are calculi that can cope with that, but most people find them very hard to read and to work with. So, my experience with industrial partners is they talk with you, they are very interested, and when you start explaining what is necessary to really apply formal method, they get more and more disappointed how much effort it is and how expensive it is. So I think there is still some way to go and some research to do with the formal methods. I mean, somewhere the industrially used languages and the formal methods can meet, but I think the industry will be ready to use formally defined language if it doesn't feel like a formally defined language anymore. So if we give them a language that has formally defined semantics in the background, I mean, that's basically what program verification frameworks do, right? That they use the program verification framework, they put in their C code, and they don't see that there is an interpretation, a formal interpretation of the semantics happening in the background. And that's probably where we can maybe get there. I don't know whether this answers your question, just some thoughts on this.
No, it does. Thank you very much. Like from the, I guess, more limited experience than I have with industry, yeah, it's really a struggle to convince engineers to go with the more formal semantics. But yes,
Yeah.
like I think accessibility is like definitely something that more research, more work has to be done on that. Thanks.
Thanks.
Okay, thank you. So any final question from anyone in the audience? Sabine, you have a question.
It was a very nice talk.
Oh, you are maybe your voice is very
Is it okay now?
soft.
Yes,
Yeah.
much better.
Okay.
We can hear you now. Yeah.
Okay, thank you very much for this wonderful presentation. Formal verification is also one of my, interested topic that I am quite, interested in, knowing that I'm working in this reliability and, hardware faults and those things. I have a question related to, the real world deployment of your approaches. So one is like verified model, and then another one is like that you would actually implement it in your embedded system thing. So I just want to know that how well does the approach transfer from verified model to the actual embedded implementation? So like more like model versus the reality, what is the gap? And
yeah, this was one of the under construction items also. Thank you for this question, which I reduced the slide. But it's an open question too, right? There is, I mean, if we consider modeling languages like System C and Simulink, there is still some way to go down to the final implementation. And at least the work we are doing does just not consider the final implementation. Maybe the runtime monitoring things are a step into this direction. But this is also a very open question. How can we make sure that the final implementation still is the same as we have modeled and verified in our modeling language? Yeah.
Okay, I see.
I cannot say much more about this. I mean, of course, there are a lot of work has been done on formal methods-based testing also, and to close this gap. But the gap is still there and serious.
One short question. So
Yes.
in your research, like what types of like safety properties that you saw, which is still it's very difficult to verify in general in research and or maybe in your approach, in your experience, so to say?
Yeah. That depends very strongly on the verification techniques we use. As you have seen, we use a variety of verification techniques. And I've shown today that for deductive verification, these global properties are very difficult. Those, of course, are more natural for model checking, right? Because that's what model checking is focused on. But for model checking, you run into severe problems if you have data. So with model checking, we always had to strongly abstract from the underlying data to make it feasible at all. So I would say the kind of properties we are interested in, like, for example, an anti-lock braking system reacts in a given time limit, or some data is correctly transferred over a bus system, or these typical system properties, they provide different challenges for different verification approaches.
But the anti-lock braking system also has some other routes why that happens. It also connects to the unreliability or the reliability threats that can emerge from the hardware. for example, some of the issues probably in control, I don't know. So how would you separate that? Like, I mean, one is safety, another one is reliability.
Yeah, I mean, if you talk about if we are using the same terms here, then reliability is the more quantitative aspect, right? And we are collaborating with Anne Remke and Erika Abraham right now to basically combine a deductive verification approach with stochastic analysis to get the quantitative aspects into the picture. And this brings similar challenges like combining deductive verification and model checking, because there you also have a state space explosion problem in another sense very quickly.
Yeah.
And in particular, we have realized that these quantitative analysis techniques I'm talking about now, I know there's a huge variety, and I'm not an expert in this field, but the ones we are using in this collaboration, they use flow pipe constructions and reachability analysis and things like this. And this is only feasible with even fewer variables than I'm used to from model checking. And in particular, we look at hybrid systems. So the differential equations need to be very simple to make the analysis feasible. So yeah, I'm not sure whether this answers part of your question, but we are working in this direction too. And I think there are a lot of open issues to work on.
Yeah, and also blurry lines somehow in between these two things. Yeah. Okay, thank you so much. Thank you.
Thank you. So I would like to thank Paula again for this great talk and a nice discussion afterwards, I would say. And of course, thank you for the remaining attendees for being here. And hope to see you all again at the next colloquium in 11th of March, where Claire Mathieu will be the speaker. So see you all, and have a nice evening, I would say. And thank you again,
very
Paula.
much. Also, thanks for the nice sharing. Thank you very much, and thanks for all who have listened patiently. Thank you.
Absolutely. Thank you.
Thank you so much. Bye-bye.
Bye-bye.